Hello, good morning and welcome to First Ring. Friends, this is the new look of your channel Electronics First Ring. In our previous class, we learned that diode behaves as a switch also, and in forward, in reverse and in zero bias condition, its behavior is different. So that should be the only behavior in these three conditions. So guys, ये जो डायोड है ये एक ऐसा बिहेवियर भी करता है which we don't need. जैसे कि हम बच्चों से कुछ ऐसा बिहेवियर हमको कभी कभी मिलता है जो कि हमको नहीं चाहिए. So that behavior in diode is called capacitance. ये डायोड कैपेसिटेंस भी ऑफर करता है and these are of two types. Let us understand. That is, one is diffusion capacitance, second one is transition capacitance. And what is diffusion capacitance? As you know, with this slide we will understand what is diffusion and what is transition capacitance. So friends, let me take the marker. So as you know, this was diode and here it was depletion layer. Now can you understand, this looks like a capacitor also. How? This is one plate, this is another plate, and this depletion layer behaves as a dielectric. As you know, in capacitor there are two parallel plates and dielectric in between. So here also it seems that this is a capacitor because this behaves as plate, these N and P, and this dielectric or depletion layer behaves as a dielectric. At lower frequency it does not show significant behavior of capacitor, but at higher frequency it offers some capacitance. So what is diffusion capacitance? When it is in forward bias condition, what happens? It was connected like this in forward bias condition, P, and this was positive. So it was forward bias. So in that condition, we learned that this depletion layer was thinner, very thin. It means the distance between these two plates N and P, just think that this is capacitor now because it is behaving as a capacitor also at higher frequencies. So when the distance between these plates is less, means as you know, in forward bias the distance was very less. So when distance is less, it offers more capacitance. As you know, capacitance is inversely proportional to distance between the plates. Means when distance is more, capacitance is less. When distance is less, capacitance of this particular diode is more. That is the basic concept of capacitance. So here also in forward bias condition, as you just apply this forward bias, so this distance is less and it means it will be offering more capacitance and its value increases with frequency. Another one, capacitance is directly proportional to frequency also, applied frequency. So when frequency is increasing, capacitance is also increasing. And in forward bias condition, capacitance is inversely proportional to distance. So this is the basic of any capacitor. It means when distance in forward bias is less, it means capacitance will be more. And same way, and this capacitance offered in forward bias condition is called diffusion capacitance. And what is transition capacitance? Same way. When this diode is connected to a battery in reverse bias condition. Now see, you think this is P, this is P, this is N. Now see what will happen, this gap will increase, means the width of depletion layer will increase in reverse bias condition, and it means when distance is increasing, capacitance will be less, and in reverse bias condition the capacitance becomes less, and this type of capacitance called transition capacitance. Now let us see next behavior of diode, that is the current flow in this diode when we apply the voltage, how current flows, how current increases or decreases, and how it behaves. Just see in this slide. Now see, this graphs looks very nice, bit hazy also. So, but we need to understand only. So guys, let us see. This is x-axis. This is shown by voltage, forward bias voltage, and this is reverse bias voltage, and this is forward current, and this is reverse current. As you know, this side it is reverse current, this side it is forward bias current. Now see, this is a diode biased in forward bias condition. This is P, this is N. Now this is the positive pole of the battery. It is connected to P side. When this is forward bias, what happens? It is seen that in forward bias condition, this graph will work. This graph आप लोगों को दिखाई दे रहा है, this graph. हम जब इसका वोल्टेज बढ़ाएं, सपोज यू हैव अप्लाइड 0.1 volt battery. So what will happen? There will very less flow of current in the circuit. See, you are increasing this forward voltage. There is very less current flowing in this. Again, you are increasing little more. There will be again slight increment in the current, and for some particular voltages. And here it is. Soon it reaches to 0.3 volt. What happens? There is exponential growth of current, and the point at which this current increases exponentially, this voltage is called knee voltage. So this particular 0.3 volt is knee voltage for germanium. So same way for silicon also, there is knee voltage at which this voltage will increase exponentially, that is 0.7 volt. And what happens? And current, it means when voltage is increasing, current will increase exponentially. Now you connect this battery in opposite direction. Now forget this. Let us understand this side. This is N and P. This is N, this is P. Here now we have connected it to reverse bias. This is reverse bias now. You know this is reverse bias. So what happens? In reverse bias, there is very less flow of current or minimum flow of current or negligible. That's why it is called reverse saturation current, because magnitude is very less. See, when we are increasing the voltages, this is reverse voltage. Now see, this is reverse voltage and this is reverse current in reverse bias condition of this diode. So what happens when we are increasing the reverse voltage? There is no increment in the current, very less, or you can say it is negligible, very less. And suddenly one points come when this diode conducts abruptly. There is sufficient increment in the reverse current, and chances are there that this diode may get damaged because of this abrupt high current. In suddenly there will be increment in reverse current, and this diode can get damaged at this particular point, and this point is called Zener breakdown point. This effect is called Zener effect. So guys, here we understood what is Zener effect, and this particular region here, this is called Zener breakdown region. So for different material, this Zener breakdown point is different for different kind of semiconductors. So today we learned about Zener effect and the behavior of diode in VI curve. It means how will be the condition of how current will increase with respect to V. Here, as we already discussed, the germanium knee voltage is 0.3. Means at this particular voltage, germanium made semiconductor or diode will conduct at this particular point. There will be exponential growth in current. And for silicon, it takes 0.7 volt. Means जब तक ये वोल्टेज यहाँ तक नहीं आएगा, सिलिकॉन डायोड में करंट फ्लो ठीक से सफिशिएंट नहीं होगा. Soon it reaches at 0.7 volt, it will increase exponentially, And same way here in reverse bias also, germanium gets Zener effect much earlier than silicon. Here in reverse bias also, the Zener voltage of germanium is less than silicon, at which the flow of current in this circuit is abrupt. So this was the curves of silicon and germanium. What will the current in the circuit when we gradually increase the voltage in forward as well as in reverse bias condition. So today we learned the curves of silicon and germanium in forward as well as in reverse bias and what is the Zener effect. So hope you understood this concept very well. So next वीडियो हम आपके लिए जल्दी से लाएंगे. So आप लोग रेडी हैं तो बताइए we are ready और नीचे कमेंट कीजिए and if you like the video just give a thumbs up and subscribe and friends share it to your friends. Thank you so much.